Hello, so today we are doing this problem called find largest value in each tree row. So the problem says we need to find the largest value in each row of a binary tree. So for example, for the first level here is 1, so we put 1 there. In this level, the largest value is 3, so we put 3 there. And in this level, the largest value is 9, so we put 9 there. And so that's the problem. And so how can we solve it? So it's a tree and we are looking for the largest value in each row, which is essentially the largest value in each level, which makes us think immediately of BFS, because BFS does the traversal by level. And so let's think about how can we implement it using BFS. So we can just do normal BFS, but since BFS every time gets a level in the queue, we can just, when we're iterating over the queue, get the max each time of the content of the queue, because the queue with BFS will contain just the current level, right? So let's see how would that look like, right? So let's look at how would that look like here. So we know that we need the result that we need to return, which is just the largest values, right? And then we know we need a queue for BFS, right? And we know we need to initialize the queue with root first, right? With the first node, first level, right? And so just the original, we can just do the general template of BFS, which is going through the queue. And since we said that the queue, for example, here contains the first level, at the second iteration it will contain 3, 2. So we can just append to the result the max of the current level, which would be in the queue. You would see I would replace here, I would put in the queue the next level, so that when we go through the while loop again, what's in the queue is only the next level from the level that we are at. So now that we are at this one, we'll take the max of the current level, which is the content of the queue. So that would be just max of node.val for node in queue. And we will start the next level. Let's call this one let's call next level queue. And that would be, we'll initialize it, and then we'll put values from, if we are, let's say, at this level here, what are the next level values? It's the children of each node in the current level, right? And so these children, we can just get them by going by going through the nodes in queue. And then for each node, we go through their child. So for child in node.left and node.right, those are the children. And we check if it's not empty, so if it's like a real child. So we can say if child, which means it's not a leaf, so it has like a value. And so at that point, we'll add it to this next level queue. And so we would append the child here, and at that point we can just do what I said here, which is initialize the queue to this new level, next level, which is this, right? And then at the end we can just return our result, and that's pretty much all there is to it. So let's see how this would work. Okay, so looks like it's alright, so I'll submit. Okay, so of course we have a problem here with the root, so I need to check if not root, so that if it's null, we can just return like nothing, res, right? So let me try it on that input. And it's empty. Now let's see, what can we do else? So yeah, let's submit and see if it works. Okay, so now it passes. Now there is something I don't like about this. Like whenever there is an if, it kind of makes the code a little bit harder to like understand right away. So instead of doing this, I can comment this part here and not need to check if the root is empty, because I will do any queue. What does this any queue do? So let me show you here. So if queue contains, let's say in the case where this one is none, empty, then in that case our Q would contain just this, right? So what is the value of any Q in that case? So any basically returns the value, returns true only if its iterable has some value that is not none. But if the Q has only none, then any would be false. So now if I put a value in my Q, let's say 1, then any Q would be true. And so by doing this, I can essentially not need to do this, and at the end I will return a res which is already empty, and basically handle this with one line of code, right? Okay, another thing also is this if a child here, I can actually just say, let's say all this stuff here, this next level, since I construct it and then just add values to it, instead of doing this entire thing, I can just simplify that by doing the following here. So I can just take this next level Q, instead of adding one by one, I could just say this and use a list comprehension, right? So I need a child, that's what I need to add to the list. For I need the node to be in Q, right? And what is the child? The child is in node.left and node.right, right? And since this is a list comprehension, I can add the check right away here. So if child, and that's about it. That's the next level, right? And also, since I'm just assigning and then assigning it again, I can just get rid of this line and just put here, right? So let's run this and see if that works. So that works for the empty case. Let's see if it works for the other case, which is which I lost the construction of it. So let's just like submit and see. Okay, so that passes. So this makes it really easier to write. Hopefully also a little bit easier to read, but yeah, so this simplifies this code. Now, we can even, let me see. Okay, so now that's BFS, so we can also solve this problem with DFS. Let's see how. So let's try to solve this with DFS. So DFS, so still we need this, and then we need to call our DFS. So what we can do basically with DFS is, while we're going here, keep track of level. So every time you go from here to this one, say now the level is 1. When we go here, the level is 2. And in our res, just have it indexed by 0 is the first row. It is the first level. 1 is the second level, is this level, and 2 is this level. And every time we encounter an element, if it existed before in res, then we just replace it if it's bigger. Otherwise, keep the value that we had before, right? And so that would work for all cases. And so what we need is, we set level, and then which starts out as 0, and we need to pass res. And then at the end, we can return res, right? And so let's define our DFS. So our DFS would get node, and then level, and then the result to append to it. And so what happens for DFS? So if the node doesn't exist, then we can just stop there, right? Otherwise, we have one thing is, if the value already doesn't exist yet in res, then we just need to append it. So if it's the first time and we are touching 3, there is no need to take the max with something else, because there is nothing else in this level that is already added. And so how can we discover that? Just by looking at length of res and checking if it's less or equal than level. Because if we are at this, let's say if we have added only for the first level, for this level, then the length of res would be just 1, and so we haven't reached this one yet. And so at that point we can just add, otherwise we can do something else. So at that point we can just add the value right away. But otherwise we need to replace, if the value, say for example at 5, and we already added 5 and 3 by doing DFS for 3. Now for 9, we need to replace the value at level 0, 1, 2 at level 2 with the value 9 because it's bigger. And so how can we do that? Just by doing res level, since that's the index, and since we are starting out at 0, so it's fine. And we will just replace with whatever is the bigger value. So level and not data. And then at the end we would return, we need to go traverse also the left and the right? So we need to do DFS on node.left level plus 1 since we are going down 1 level, and res, and we need to do the same thing for right. And that's pretty much it. Okay, so it works with that one. Well, this one is empty, but yeah, so it passes on this one too. So that's all for now for this problem. See you next time. Bye.